complex numbers and fractals. Today, we are diving into the fascinating world of fractals. But first, what exactly is a fractal? Fractals are complex, self-repeating shapes that appear at every level of magnification. Think of branching of trees, the patterns on a snowflake, or the curves of a coastline. These are all examples of fractals in nature. In mathematics, fractals are created using formulas that repeat infinitely, creating shapes of unimaginable detail and beauty. In this video, we'll explore how complex numbers are used to generate fractals, break down the math behind them, and show you the code that brings these intricate designs to life.
To understand how fractals are made, we first need to understand complex numbers. Unlike real numbers, complex numbers add a new dimension. They're written as a plus bi, where a and b are real numbers and I is something special. I is the imaginary unit representing the square root of
-1.
While this might seem strange, it opens up new possibilities in math. A complex number like 3 plus 4i can be represented as a point on this complex plane, where the real part 3 is on the horizontal axis and the imaginary part 4 is on the vertical axis.
Now that we know about complex numbers, let's see how they're used to create fractals. A fractal pattern emerges when we apply a simple formula repeatedly. That simple formula is z equals to z squared plus c, where this z will be a complex number. But for simplicity, let's do a real number example to show how the computation works. If we start with z equals to 0, and let's say c is 3, we compute z1 by squaring 0 and then plus 3, and we get 3. And to compute the next number, we square again and then plus the constant c. And what we get is 12 here. And if we repeat this process over and over again, if z stays within a certain bound, then this point or this complex number belongs to the fractal. But if z grows too large, it escapes and doesn't belong to the fractal. This process of iteration, repeating a simple formula over and over again, reveals complex, self-similar shapes, where each part of the fractal resembles the whole, no matter how much you zoom in. This is the essence of a fractal.
Let's break down this iterative process using code to calculate the color of each pixel in our fractal image. Each pixel's location acts as a complex number input for the formula z equals to z squared plus c. So say we focus on this pixel, which could be of the coordinates 3, 10. We apply this into our formula, which is z equals z squared plus c. We repeat this calculation for each point in our image until z either escapes or remains bounded. We then count the iterations it took for z to escape, and this count determines the color of that pixel. Now comes the artistic part, coloring. Each pixel's color depends on how quickly z escaped. Let us use 255 to be white and 0 to be black. In essence, if z escapes quickly, it gets a warmer color, red, orange, or yellow. If it takes longer, cooler colors like blue or purple. Pixels that never escape remain dark, adding contrast to the fractal structure. The color choices help make the fractal visually striking.
Here's the code of computing the complex numbers for each pixel. As we talked about before, we iterate through each of the pixels, and then we assign a complex number based on its coordinates. And then we call the Julia function, which then computes the numbers z based on the formula that we introduced before. And we do this iteration until either there are more than 255 iterations, or if z goes beyond 4, z squared goes beyond 4. And we count how many iterations there are before we reach either of these conditions. And if iteration is equal to 255, that means that this condition was met first before our z gets too large. So what it means is that when we compute the z, it actually stays within a bound without going too large. And in this case, our complex number is converging or periodic. Another case is that our iteration is less than 255. And what it means is that this condition, which is when z goes too large, is satisfied before our I can even reach 255. And in that case, we know that our z is growing rapidly and is escaping. By doing this code, we're able to find out if this pixel with value of z is converging or is escaping. And we use this information to calculate or to assign a color for that specific pixel, like what we see right here.
What we end up with is a fractal, an infinitely repeating structure generated from a simple formula. This is the magic of fractals. A simple rule repeated infinitely creates unimaginable complexity. No matter how much you zoom in, the pattern remains detailed, showing self-similarity. And the colors? They reveal each pixel's journey through our formula, adding life to the math.